July 2019, Goddard Space Flight Center, Greenbelt, Maryland. A 17-year-old from New York City sat at a government workstation. Third day on the job. Summer internship. Everything still new and unfamiliar. His name was Wolf Zucker, high school student, not yet old enough to vote. Around him, astrophysicists with decades of experience moved through their routines. He had been assigned a task that seemed straightforward. Look at light curves. Graphs of stellar brightness over time, downloaded from NASA's newest space telescope. Somewhere in those graphs, planets might be hiding, waiting for someone to notice. He did not know that by the end of that day, the universe would give him an answer. Not a simulation, not a homework problem, a real planet orbiting two real suns. The story of how it happened says something profound about science, access, and attention. The Transiting Exoplanet Survey Satellite launched April 18, 2018 from Cape Canaveral. A SpaceX Falcon 9 carried it into a unique elliptical orbit high above Earth. Unlike Kepler before it, TESS would not stare at one patch of sky indefinitely. Its 4 wide-field cameras divide the sky into 26 sectors observed over 2 years. Each sector receives 27 days of continuous observation before the cameras shift onward. The mission's goal was focused. Find planets orbiting the brightest, nearest stars. Not distant, faint targets like Kepler studied, but nearby suns we can examine closely. TESS searches for transits, the tiny dimming when a planet crosses its star's face. A Jupiter-sized planet blocks roughly 1% of its star's light during each passage. An Earth-sized planet blocks less than 0.01%. A nearly invisible flicker in brightness. Detecting these signals requires staring at thousands of stars simultaneously for weeks. TESS produces roughly 20 gigabytes of data every 13.7 days as it completes its orbit. In its first year alone, the telescope identified over 280,000 candidate events. Most turn out to be false positives, binary stars mimicking planetary transits precisely. A planet requires at least 2 transit events to confirm that periodicity is real. Behind the automated detection pipelines, humans were still needed to check the data. Not just professional astronomers, but anyone curious enough to look with care. In 2010, a group at Yale University launched a project that changed citizen science. Planet Hunters, a website where anyone could analyze real Kepler telescope data online. No degree required, no professional training, just a computer and genuine willingness. Volunteers worldwide classified light curves, marking where brightness dips appeared. Their collective effort found planets that automated algorithms had missed entirely. The human eye, it turned out, notices patterns that computer code does not always catch. When TESS launched, the platform expanded and became Planet Hunters TESS. Same concept, new data, fresh sky, and hundreds of thousands of new light curves waiting. By 2019, over 28,000 volunteers worldwide had registered on the platform to contribute. Teachers, truck drivers, retirees, students, all helping to advance genuine science. The data was real, the stakes were real, and occasionally the discoveries were real too. Wolf Zucker arrived at GSFC with a background unusual for a summer intern. He had studied astronomy independently, read research papers, attended science programs. But reading papers and contributing to them are separated by a gulf most never cross. His supervisor was Dr. Veselin Kostov, a SETI Institute scientist based at GSFC. Kostov specialized in circumbinary planets, worlds with not one sun, but two above them. He had published extensively on how binary star systems interact with orbiting worlds. The assignment seemed routine. Examine flagged light curves, note anything unusual. Wolf opened his first data file on the morning of his third day at the facility. On screen appeared the brightness record of a star called TIC 2601283333. The system sits approximately 1,300 light-years away in the constellation Pictor. What should have been a simple pattern became something far more complicated at once. Binary star systems produce complex light curves that confuse both humans and algorithms. When two stars orbit each other, they periodically eclipse one another from our view. Each eclipse produces its own characteristic dip in total brightness measured from Earth. The two stars in TIC 2601283333 orbit each other every 14.6 days in a tight ellipse. Their mutual eclipses create a repeating sawtooth pattern, regular and mechanical. Automated TESS pipelines had flagged this as a binary and largely set it aside. Binary stars were not the prize. They were noise obscuring potential planetary signals. Wolf stared at the light curve, tracing the familiar binary eclipse signatures across it. Then something stopped him. A dip that did not fit the established repeating pattern. It was shallower than the stellar eclipses, shorter in duration, differently shaped. And critically, it appeared only once in the first sector of available TESS data. A single anomalous event in a complex light curve could easily be a measurement artifact. Most interns would have noted it carefully and moved on to the next file in the queue. Wolf Zucker went looking for a second occurrence instead of moving on. He pulled data from additional TESS sectors covering the same region of sky. The TIC 2601283333 light curves extended across multiple observation periods over months. Within those additional files, buried beneath the regular binary star pulsation, it was there. A second dip, same depth, same duration, same distinctive shape as the first event. Two matching events separated by time, neither fitting the known binary eclipse pattern. In transit photometry, two matching dips suggest a periodic process, potentially a planet. The spacing between the events yielded a candidate orbital period for calculation. Wolf ran the numbers. Approximately every 95.17 days, something crossed one of those stars. But here was the complication that made this system uniquely difficult to read correctly. In a binary star system, the gravitational landscape shifts constantly as the stars orbit. A planet circling both stars does not follow a simple, fixed elliptical path through space. Its orbital period varies slightly each cycle as the binary configuration changes beneath it. These transit timing variations, astronomers call them TTVs, can be large and irregular. A circumbinary planet might arrive at transit 30 hours early in one orbital cycle, then 40 hours late in the next, then early again, never precisely on schedule. Automated algorithms search for rigid periodicity, evenly spaced signals repeating in time. A circumbinary planet's varying timing renders it nearly invisible to standard detection code. Human eyes, following shape and depth rather than strict timing, could still find it. Wolf had done exactly what the automated systems could not, recognized the signal by sight. Recognition is not confirmation. In science, the distance between them is enormous. Wolf brought his finding to Dr. Kostov, laying out the two transit events side by side. Kostov examined the data carefully, running through the standard checklist of false positives. Could the signal be a background eclipsing binary contaminating the TESS photometry? Could instrumental artifacts be mimicking the shape of a genuine planetary transit? Could the signal represent a third star in the system rather than a planet at all? Each alternative hypothesis required its own analysis, its own tests, its own elimination. The team requested archival data from other observatories that had covered the same field. TESS provides wide pixel resolution, large enough that multiple stars can contaminate data. High-resolution ground-based imaging was needed to isolate the host stars with precision. Ground-based follow-up photometry was arranged during the timing of a predicted transit. The transit occurred as predicted, confirming the signal was real and tied to the system. Spectroscopic data confirmed the binary nature of the host stars and their orbital parameters. The orbital solution tightened, a planet 6.9 times Earth's radius circling a binary pair. TOI 1338b had been discovered, though formal naming would follow verification weeks later. The concept of a planet orbiting two stars belongs to science fiction's most iconic imagery. Luke Skywalker watching twin suns set on Tatooine captured something real about the cosmos. Long before that scene existed, astronomers had speculated whether such worlds could form. The gravitational environment around a binary pair is fundamentally unlike anything else. Where a single star pulls planets into stable ellipses over billions of undisturbed years, two stars in mutual orbit create a gravitational landscape that shifts constantly in time. As the stars orbit each other, their combined influence rotates and pulsates across the disk. Objects orbiting too close to the binary pair get ejected or fall inward relatively quickly. There exists a critical boundary called the stability limit around every binary system. Inside that limit, planetary orbits are chaotic and short-lived over astronomical timescales. Outside it, stable orbits can persist, though they remain more complex than single-star paths. TOI 1338b orbits at 0.45 astronomical units from the binary center, just outside the stability boundary. The two host stars are a G-type dwarf, similar to our Sun, and a cooler M-type red dwarf. Their mass ratio creates a gravitational dance the planet must navigate on every orbit. The planet receives light from both stars simultaneously, 2 suns crossing its sky each day. Depending on orbital geometry, one sun can eclipse the other from the planet's perspective. Sunsets on TOI 1338b would look nothing like anything familiar to human experience. The first confirmed circumbinary planet was not found by TESS or planet hunters. Kepler 16b was announced by NASA on September 15, 2011, from Kepler mission data. Scientists, including Dr. Lawrence Doyle, spent years carefully analyzing its complex light curve. When they published in Science magazine, the discovery made international headlines everywhere. A planet orbiting 2 stars, not as science fiction concept, but as a measured, verified reality. The planet receives light from both an orange K-type star and a red M-type dwarf companion. It orbits at 0.7 astronomical units in 229 days, with surface temperatures around -73 degrees Celsius. Cold, distant, and gaseous, Kepler 16b was never a candidate for habitability of any kind, but it proved the concept unambiguously. Circumbinary planets exist, they can persist and form. Over the following decade, Kepler found a dozen more circumbinary planets in its survey data. Each discovery raised the same fundamental question the models could not yet fully answer. Planetary formation theory had been built around single-star systems, our solar system foremost. Accretion disks around binary pairs were considered too turbulent for planetesimals to survive. The gravitational perturbations would stir dust and rock before it could accumulate steadily. Every new circumbinary discovery made the theorists work harder to explain the impossible. TOI 1338b would join that list of impossible worlds, confirmed by a high school intern. Understanding why circumbinary planets are problematic requires understanding normal planet birth. Stars and their planets form together from the same cloud of molecular gas and dust. As the cloud collapses under gravity, conservation of angular momentum spins it into a disk. The central mass grows hotter until nuclear fusion ignites and a star blazes into existence. In the surrounding disk, dust grains collide gently and begin to stick to one another. Millimeter-sized grains become centimeter pebbles. Pebbles become meter-sized boulders. Boulders accumulate into kilometer-wide planetesimals over hundreds of thousands of years. Planetesimals collide and merge, growing into moon-sized bodies, then full planetary embryos. Embryos sweep up remaining material until a planet emerges and clears its orbital neighborhood. This process works beautifully for a single star with a calm, stable gravitational center. Binary star systems complicate every step of the process in different ways simultaneously. Near the binary pair, gravitational resonances stir the disk faster than grains can stick. Instead of gentle accumulation, kilometer-wide rocks shatter each other into gravel repeatedly. Planetesimals that manage to form quickly find their orbits shifting chaotically beneath them. The stability limit creates a gap where material simply cannot accumulate under any conditions. Yet circumbinary planets are found just outside that limit, right where theory most forbids them. How did they form in the very place where formation should be most impossible? The most widely accepted answer involves location shift during the planet's earliest history. The disk migration hypothesis proposes that TOI 1338b did not form where it currently orbits. The planet formed farther out from the binary pair, where the disk was calmer and denser. There, planetesimals accumulated normally, shielded from the worst gravitational disruption. As the planet grew, interactions with the surrounding disk caused it to spiral slowly inward. Type 1 migration occurs when a growing planet launches spiral density waves in the disk. Those waves carry angular momentum outward, and the planet loses angular momentum in return. Losing angular momentum means spiraling inward toward the binary pair at the system's center. Migration continues until the disk dissipates or a resonance halts the planet's inward path. TOI 1338b apparently halted just outside the stability limit, avoiding ejection from the system. This scenario is elegant, but leaves questions that current data cannot definitively resolve. Did the planet form as a single body, or as multiple smaller planets that merged over time? How long did migration take, and what stopped it at precisely the observed orbital distance? Alternative hypotheses suggest in situ formation through processes not yet fully understood. Perhaps gravitational stirring that prevents normal accretion can also enhance it locally. Density concentrations created by resonances might trap material, allowing faster assembly. Researchers at multiple institutions have modeled collisional processes in circumbinary disks. Some models suggest certain binary configurations might actually aid rather than hinder formation. Resonant stirring, under specific conditions, creates preferred collision velocities for growth. No single formation model has successfully reproduced the full circumbinary planet population. The question Wolf stumbled onto when he spotted that anomalous dip remains open today. By autumn of 2019, the TOI 1338b discovery had been fully verified across multiple datasets. The lead author coordinating the paper was Dr. Veselin Kostov of the SETI Institute at GSFC. 17 co-authors contributed data analysis, orbital modeling, and observational follow-up. Among those 17 names appeared Wolf Zucker, high school student, summer intern. For most scientists, a first co-authorship comes years deep into graduate school at earliest. Wolf received his while still completing his senior year of high school in New York City. The paper was submitted to Nature Astronomy in late 2019 after months of revision and review. On January 6, 2020, it appeared under the title Formalizing the New Circumbinary Discovery, TOI 1338, TESS's first transiting circumbinary planet. The headline was deliberately plain. The story behind that headline was anything but ordinary, and science journalists found it fast. NASA issued a press release highlighting the intern discovery story alongside the core findings. Within days, Wolf's name appeared in CNN, the BBC, Le Monde, and dozens of other publications. A 17-year-old had found a planet orbiting 2 stars, and the world wanted to know how. The attention focused on the human dimension, but the science was equally astonishing throughout. TESS had found its first circumbinary planet, and planet hunters had helped make it happen. TESS was designed with professional science as its primary objective. Exoplanets, at scale. The volume of data it generates creates opportunity no professional team can handle alone. Gigabytes accumulate every 2 weeks, hundreds of thousands of light curves piling endlessly. Automated pipelines catch most of what is detectable by algorithm, but algorithms have limits. They excel at finding regular, periodic, well-behaved signals matching their training parameters. Complex signals and irregular patterns fall below algorithmic detection thresholds entirely. Human pattern recognition evolved over millions of years to notice anomalies in the visual. Excels precisely at the signals that computers classify as noise and discard without pause. Planet hunters. TESS converts this biological capability into systematic scientific contribution. By 2024, the platform had facilitated dozens of confirmed planetary discoveries by volunteers, none more dramatic than the one a 17-year-old made on his third day at work. The lesson is not that professionals missed something obvious that an intern found by luck. The lesson is that the data stream is so vast that every careful pair of eyes adds real value. Wolf succeeded because he was careful, not because he was lucky, and that distinction matters. What precisely did Wolf-Zucker do that automated algorithms had failed to accomplish? The binary eclipses in TIC 2601-28333 created a complex, high-amplitude light curve baseline. Standard pipeline algorithms subtract the binary signal first, then search residuals for planets. The subtraction is imperfect when binary parameters are not precisely known from the outset. Residual signals from imperfect binary subtraction can mask genuine planetary transits completely. Wolf examined the raw light curve, not the processed residuals from automated pipeline work. His eye tracked the shape, depth, and symmetry of the anomalous dip independently of context. He did not subtract the binary signal mathematically. He recognized the dip as distinctly other. Depth, duration, and ingress shape all differed from both known stellar eclipse profiles. These differences were visible to human perception in ways difficult to formalize in code. After flagging the event, he searched specifically for similar events rather than for periodicity. That search strategy was adapted to the irregular timing that circumbinary planets naturally produce. He was, in effect, applying the correct search algorithm for the problem through intuition alone. He knew circumbinary planets existed and knew their timing would never be perfectly periodic. That domain knowledge guided his search in exactly the direction needed to find the hidden signal. TOI 1338b belongs to the size category astronomers call a sub-Saturn or large Neptune. At 6.9 times Earth's radius, it falls between Neptune and Saturn in physical dimensions. Density estimates from known geometry suggest it is a gaseous or mixed composition world. No solid surface likely exists to stand on, just a sphere of gas above a compressed core. The two host stars together place the planet in a zone neither scorching nor deeply frozen. Surface conditions, if a surface existed, would depend heavily on atmospheric composition. The 95-day orbital period means a year equivalent passes every 3 months by Earth count. During each year, the planet witnesses the binary pair complete approximately 6 mutual orbits. From the planet's perspective, the two stars weave complex paths against the background stars. Sometimes they appear as one fused bright point, sometimes separated by degrees across the sky. The larger G-star dominates, providing roughly 80% of the total luminosity reaching the planet. The smaller M-dwarf companion adds warmth and occasional flares from its closer quarters. Atmospheric modeling for circumbinary worlds remains in early stages, with few observational anchors. TESS photometry yields size and orbital parameters, but chemistry remains unreachable for now. JWST has not yet targeted TOI 1338b for atmospheric spectroscopy in its current programs. Future observations may reveal whether molecules in its atmosphere hint at interesting chemistry. Following the January 2020 publication, the TOI 1338 system continued attracting scientific attention. In 2021, a second planet in the same system was identified from additional TESS data analysis, TOI 1338c. This second world does not transit its stars from our current viewing angle. Its presence was inferred through transit timing variations in the original planet's light curve. When a second planet exists nearby, gravitational tugs shift the first planet's transit times. The timing variations carry information about the perturbing planet's mass and orbital period. TOI 1338c was estimated at roughly 7 to 22 Earth masses, with a period near 215 days. Two circumbinary planets in the same system, a discovery that sharpened the formation puzzle. If one circumbinary planet was difficult to explain, how did this system produce two together? Migration scenarios must account not just for one inward journey, but a coordinated pair of them. During migration, the two planets interacted gravitationally, affecting each other's trajectories. Dr. Kostov's team, with continued collaboration from Wolf, published The Second Planet in 2021. Wolf Zucker, by then a college student, remained connected to the system he first found. That continuity speaks to how genuine discoveries attach themselves to the discoverers who make them. Every generation of scientists can trace a moment when curiosity became something more serious. For some, it was a telescope borrowed from a parent. For others, a textbook read under a flashlight. For Wolf Zucker, it was a summer at Goddard Space Flight Center, staring at a brightness graph. The circumstances were unusual, the outcome extraordinary, but the underlying mechanism was universal. A person paid close attention to something difficult, noticed what others had missed, and asked why. That sequence requires no degree, no prior publications, no institutional credential to execute. It requires patience, pattern recognition, and willingness to follow a question past easy answers. Wolf did not discover TOI 1338b because he was fortunate enough to receive an internship offer. He discovered it because he worked carefully on his third day, when others might have explored campus. The discovery rewarded effort, not pedigree, and that is the story the data actually tells. Planet Hunters. TESS was designed precisely to harness this kind of engaged attention at full scale. If one intern at one workstation could find a circumbinary planet in 3 days of focused work, what remains hidden in the light curves the other 28,000 volunteers have not yet examined. The Planet Hunters model reveals something counterintuitive about modern, large-scale science. As instruments grow more powerful, data volumes increase faster than analytical workforce does. The gap between what telescopes observe and what scientists fully analyze keeps steadily widening. Citizen science platforms transform this gap into a resource by recruiting the curious public. Planet hunters. TESS volunteers collectively represent thousands of years of human attention applied. Each one brings curiosity, pattern recognition, and time that professional teams cannot match alone. Some volunteers have logged thousands of hours of data analysis over years of regular participation. They develop intuitions about what normal TESS light curves look like, making them genuinely sharper. Their knowledge is distributed, non-hierarchical, and constantly growing through earned experience. Dr. Chris Lintott at Oxford, one of the original Zooniverse platform architects, has explained this. The wisdom of crowds applies not just to opinion polls, but to complex observational data analysis. Thousands of independent judgments about the same data converge on correct answers reliably. When 90% of volunteers flag the same feature in a light curve, the real probability rises fast. The TOI 1338b discovery emerged from exactly this collective intelligence functioning as designed. Wolf Zucker was not the first citizen scientist to contribute meaningfully to astronomical discovery. In 2012, Planet Hunters volunteers identified PH1b, a circumbinary planet in the Kepler data. 4 volunteers working independently flagged the same light curve anomaly without any coordination. Their agreement across independent analyses convinced professionals to follow up with spectroscopy. The planet was confirmed, and all 4 citizen scientists were listed as co-authors on the paper. In 2017, amateur astronomer Thomas Jacobs discovered 4 young, massive planets in Kepler data. He had been analyzing light curves for years from his home, developing deep, practical expertise. Jacobs went on to co-discover over a dozen planets, building a collaborative network of amateurs. His partner in several discoveries was Daryl LaCourse, another non-professional with real depth. These examples are not curiosities. They represent systematic contribution to accumulated knowledge. The boundary between professional and amateur has become permeable in ways unprecedented in science. Platforms like Planet Hunters democratized discovery itself, not just access to observation results. A 17-year-old with no degree or publication history could contribute genuinely and directly, not through luck, but through applying the skills science rewards most: sustained, careful attention. There is something worth pausing on in what happened that July morning in Greenbelt, Maryland. A space telescope 1 million miles from Earth sent data to a government facility on the ground. That data was made freely available to anyone with an internet connection through a public platform. A high school student found a planet orbiting 2 stars 1,300 light-years away inside that data. The chain connecting cosmic distance to human discovery ran through open access and shared data. Had TESS observations been proprietary, reserved for funded researchers who built the telescope, Wolf would have looked elsewhere, and the planet might have waited years longer for its discovery. The commitment to open science, to making raw observations accessible beyond institutional walls, created conditions where a 17-year-old could contribute to humanity's knowledge genuinely. This is not an administrative detail about data sharing policy. It is a philosophical statement. Science belongs to the species, not to the institutions that fund it in any given decade. Publicly funded observations describe a universe that predates every funding cycle by billions of years. Making those observations accessible is not generosity, it is clarity about who owns knowledge. About 1,300 years ago, the light Wolf would one day discover left its twin star source in Pictor. Two stars orbited each other in that constellation, while a gaseous planet circled them both. That light traveled through empty space for 13 centuries before arriving at a TESS detector. It was captured, digitized, transmitted to Earth, stored on servers in Greenbelt, Maryland. Made publicly available through a platform designed to distribute the task of understanding it. On a July morning in 2019, a teenager looked at it and saw what no one else had caught. The photons did not care how old their discoverer was or what school he attended. Physics is democratic, indifferent to the status of whoever describes it correctly. TOI 1338b orbits its binary stars, whether or not anyone ever confirmed its existence from Earth. The planet did not require our discovery to be real. It existed long before we evolved. Discovery transforms a cosmic fact into a human fact, something known and something named. Wolf Zucker made a piece of the universe real for humanity in a way it had not been before. That transformation from unknown to known is what every scientist chooses as their work. The age at which it happens matters less than the care brought to the examination itself. On the third day, at a government workstation, staring at a graph of stellar brightness over time, a 17-year-old from New York City contributed a line to the story of the cosmos. Two stars 1,300 light-years away, unaware of being observed, continued their ancient orbital dance. The planet between them traces its own path, measuring time in 95-day increments without pause. Neither the stars nor the planet needed our attention, but we are richer for having paid it. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.